Hello, and welcome to the new paradigm for our course, Physics for Future Leaders, Physics 120 at Cal Maritime. So, the two lectures prior to in-person classes being canceled, etc., had to do with climate change, and attendance of those two lectures was pretty spotty. Different sets of people showed up to different lectures, and so I'm not really sure that anybody got all of this material. And so I decided to commit some stuff that some of you have already seen to a video so that everyone would at least have a baseline to work with, and then we'll add new material in the very near future so that we can start moving through this topic. I know this isn't ideal, this situation, and if I had had more time to prepare, maybe things would be a little more polished. But I appreciate your patience and understanding, and we will do the best we can to get you the education that you deserve. So, with that preamble, here's a slide that is the very first thing we're going to talk about with climate change. And the thing that drives climate change at its core is the greenhouse effect. And we want to answer the question of, first, why does the greenhouse effect happen? Because although climate change itself and many aspects thereof is politically controversial and has profound effects on policy and government and humankind around the world, the basic physics of it is pretty non-controversial. So let's start with that, and then we'll branch out into some of the other more thorny areas. So what we're looking at here, and let me get my pen up here, okay, is the solar spectrum. We saw this before when we were talking about electromagnetic radiation, and we have essentially power on the y-axis, so watts per meter per nanometer. Anyway, so concentrate on the watts. And so our peak power is right about here. This red yellow curve, remember, is the measured solar spectrum at the top of our atmosphere. So before it hits the atmosphere, and some of it is absorbed by all the different gases and all the different constituents in our atmosphere. And if you then compare that yellow spectrum, which peaks in the visible, right about in green, about 400 nanometers, so green light. If you compare that to the red, you can see that all across the board our atmosphere does a good job of scattering whole bunches of light energy from the sun. So everything is reduced. But there's certain places, for example, here, just outside of the visible, let me get a different color. Purple, nice. So here, just outside of the visible spectrum in the infrared, you can see there's a very sharp absorption line that is associated with atmospheric oxygen, so O2. And that's because one of the little vibrational modes can be excited by a very specific wavelength in the infrared. And so that gets absorbed by O2, and so we don't measure it down here on the surface of the Earth because there's lots of O2, atmospheric oxygen, in the atmosphere. And then you see other holes in the spectrum from various bits of H2O and CO2 and more H2O over here and more stuff by H2O over here. As it turns out, H2O is a very powerful greenhouse gas in itself, in addition to CO2 and some others. Okay? But all these little holes in the spectrum is places where the stuff that makes up our atmosphere is particularly good at absorbing the light that comes from the sun. And that, as it turns out, is both a good thing and a bad thing, depending on how much of those things that we have in the atmosphere. So why does the greenhouse effect happen? Right? As we just talked about, certain atmospheric gases absorb infrared radiation. They then re-emit it, and those photons of light are repeatedly absorbed and radiated and absorbed and radiated, and that effectively traps this infrared radiation, which results in heat, near the Earth's surface and in the lower atmosphere. So, this little animation does a pretty good job. This is courtesy of NASA. You can see the little citation down here that they've stamped on their Giphy. And what you can see there is that solar radiation comes into the atmosphere, and it comes in, it is absorbed by the Earth's surface, by some of the stuff in the atmosphere, and re-radiated as heat, as infrared photons that get absorbed by all kinds of stuff in the atmosphere and on the Earth's surface. So greenhouse gases include carbon dioxide, we mentioned that one. We've mentioned also water vapor, that's a greenhouse gas. So things that increase the proportion of water vapor in our atmosphere tends to drive the greenhouse effect. Other chemicals that aren't as well known as greenhouse gases are methane and chlorofluorocarbons and nitrous oxide, as well as some others, though those are the biggest offenders in that short list. And this effect is the primary driver of climate change and is present on this planet and others. So if we didn't have the greenhouse effect, well, we'd be a lot colder than we are now. All of the stuff that came from the sun was just perfectly radiated out into space. We'd be much, much colder, the average temperature of our Earth. And other places, well, we'll look at those, okay? And it is worth saying at this point, just so we put across this point first and last and everywhere in between, is that the scientific community generally agrees that anthropogenic, so human activities, have driven the relatively recent increase in global average temperatures. Now, I'm not just going to leave that there. We're going to talk about more about why it is that we know that and why we're so certain that we have had a hand as humans in driving up global temperatures in the last 100 years or so. Okay, just as a side note, the greenhouse effect on other planets, there's two extreme examples. There's Mars, because the atmosphere is thin there. It's actually mostly made up of CO2, but because it's so thin, very little solar energy is trapped, and so surface temperatures are very low. If it had a greenhouse effect more like ours, or even greater, you could actually think about Mars having temperatures that would be habitable by some sort of life form, but so far we've discovered no Martians, and that's partially because the temperatures are very low on the surface of Mars. You can have solid CO2 precipitating out of the atmosphere most days, and that stuff is very cold. Now, on the flip side, you've got Venus, where the atmosphere is very thick and made largely of greenhouse gases. A lot of CO2, a lot of methane, and surface temperatures are enough to liquefy lead. It's also a very thick atmosphere, so the pressure at the surface of Mars, like on the ground, is equivalent to being a mile deep in one of our oceans in terms of the pressure that we would feel there. So actually directly observing the surface of Venus is a very tricky thing, both because of the pressure and the temperature. But it's an example of what's called the runaway greenhouse effect, where there's this self-reinforcing process where it traps heat, and that heat raises temperatures and it drives more CO2 out of the rocks on the surface into the air, and then that traps more heat, and it's gotten to sort of a steady state where, well, the temperatures are enough to liquefy lead, and we certainly wouldn't want to be in that kind of situation. Now, of course, we're nowhere near being in one of these extremes, but it is important to note that the greenhouse effect is this general physical process that occurs in all kinds of places. Now, back to Earth temperature-wise. Temperature records since, well, we had reliable thermometers, so back maybe 100 years before the current day, all the temperature records generally agree. And you've got a list of 5 major institutions that keep track of average surface temperatures on the Earth by various methods. So some of them are related, they're not completely independent, but we have 5 different methods of arriving at these temperatures that all are generally in pretty good agreement. You have some variation, more variation typically in the closer you get to sort of the beginning of our modern temperature record. But as we get more and more modern, the less and less disagreement there is. And so we have this run up in temperature, admittedly only at this point over sort of a average baseline that was inserted here. You see this gray line, that's sort of our baseline point. But we're up over a degree in about 40 years. And a degree might not sound like a lot, but that is a lot of heat energy when you spread that all across the globe. And that is a problem for all kinds of reasons. Okay? Now, as far as establishing the temperature record, that's a very important thing because we want to be able to compare what our temperatures are now to historical temperatures. So we know whether or not this is anomalous, right? This is unusual, or whether this is something that is cyclic or whether this is cooler than usual. All these kind of things, all these kind of questions you start asking when scientists see this run up in temperature. Now, the farther back in time you go, well, we don't have temperature. Sorry, rather, we do have temperature data, but it's all by what's called proxy. And that's because we don't have thermometers sitting around in the medieval ages, in medieval times, in the Middle Ages, taking measurements. We have to infer the temperature based on all kinds of other things. And we will talk about in later presentations about ice core data and tree ring density data and fossil records and all sorts of other things that allow us to go back. Well, in this graph, we're going back to 1000 AD, okay? Or CE, I guess is the more current era, right? Domini. Anyway, so back to more than 1,000 years, and attempts have been made, though you get less and less precision and less and less accuracy and precision as you go back farther and farther in time, is something like this, where studies have tried to infer by proxy data what the temperatures were on the Earth way back. I mean, look at this scale. Way back millions of years before the present, so 500 million years before the present, we have guesses at least about what the temperature was like. And so we're going to talk about how this is done as well, briefly, but I just wanted to show you the extent to which we have studied the temperature record of the Earth and tried to establish what it is that's happening here in the so-called modern day. Okay? So, what we're going to start with in the next video are the drivers of climate. In other words, what are the things that drive the greenhouse effect, which in turn drives the run-up in temperature that we see. And the prime suspect early on in climate scientists was CO2, and that remains one of the most important greenhouse gases that scientists study. And we're going to talk a little bit in the next video about why we think that carbon dioxide, among other greenhouse gases, are driving temperature and not the other way around or something like that. And we're also going to talk about how it is that we build these proxy records of temperature so that we can tell that what we're experiencing now is going to be outside the experience of something that humans have ever really experienced, particularly in the modern age. So thank you for your attention. Sorry if this first video is a little rough, and hopefully we'll get a little bit better at this. I will get a little bit better at this as time goes by. Thanks for viewing.